Welcome to the course of Linear Algebra and Applications. This course is part of the teaching unit Advanced Control 1, and this course is at the service of other teaching units, of course Advanced Control 1, but also Advanced Control 2, Dynamique des systèmes mécaniques, Commande et interfaçage des systèmes électriques, and System Identification. This online course covers the theory, but will also present some associated exercises which are solved directly. The exam will be focused on applications of the course in exercises. There will be separate exercise sessions to train you for this exam, either at ECAM or via virtual means such as Teams. In order for those sessions to be effective, you should of course view the related videos before the exercise session. You will be informed of the exercise sessions in due time. As usual, if you see typos, if you have ideas on improving the course, do not hesitate to contact me, preferably by email. MATLAB is a good tool to assist you in this course. You should use it to check your results. For instance, when you're doing elimination, you can check the intermediate results using elimination matrices in MATLAB. The advantage is that you check the results and at the same time you learn to work with elimination matrices. The toolboxes covered by the student suite will be enough for this course, but as you will probably follow the course of system identification next year, you should add the MATLAB system identification toolbox. The course is based on the book Introduction to Linear Algebra by Gilbert Strang, and there is also an associated online course by this author. You might find it interesting to have a look. The link is shown on the screen. These are the notations that I will be using. So a lowercase letter in a light font will denote a scalar. Well, a lowercase letter in bold will denote a vector, and it will always be a column vector. So if you see the letter in bold with a T denoting transpose on top, this means that it is a row vector. And finally, a uppercase letter in bold will denote a matrix. So you can see that from the notations you can actually see the meaning of the corresponding variable. Matrix algebra is used in almost every branch of science and technology. Examples of that are, of course, control, but also estimation, identification, machine learning, big data problems, etc. In this teaching unit, Advanced Control 1, we will use linear algebra to describe multivariable systems, systems with multiple inputs and multiple outputs, and this will lead to the state space description that is studied in the second part of this teaching unit, state space control. So in chapter 2 we'll study vectors and matrices, and these are concepts that you know, of course, that you've studied before, but we'll extend things a little. So vectors you have studied in R cube, and we'll take it to Rn, and you've probably seen 3 by 3 matrices. So these are matrices that are in R 3 times 3, and we'll take it to R m times n. So these are matrices that have m lines and n columns. As I've said before, we will review basic concepts of matrix algebra, and you have encountered these concepts before, but it's important that you spend some time to fully understand the material that is presented in this chapter before you go on. And in particular, I want to draw your attention on the interpretation of the product of a matrix and a vector. So vectors are used for describing quantities with a direction and a magnitude. So when drawing a vector, the direction is given by the arrow, okay, and the length of the arrow is the magnitude. Force and velocity are often represented as vectors, as we will see in the course Dynamique des systèmes mécaniques, and vectors offer a convenient way to represent multiple variables, as we will see in the second part of the course, state space control, where we will represent the system by the state vector, a vector containing the state variables. In this course we will work with vectors in Rn. So these vectors are n tuples of elements of R. So the Vi are elements of R, they are real numbers. These Vi are called elements, components, or coordinates of the vector V. And you might also encounter the notation that the vector is in Cn, so it's an n tuple of elements in C, which means that the elements are complex elements. So here we work in R2 or R square. This is simply because we can represent things on the slide, and we represent two vectors, vector V with coordinates -1, 2, and vector W with coordinates 3, 2. And here we have chosen to represent or to locate these vectors at the origin of the reference frame. Okay, but vectors are not located at a specific place, so we could, for instance, locate these vectors at another spot, for instance over here, and then you obtain two equivalent vectors. Okay, that are located at this given spot. They are equivalent in the sense that the direction is the same, okay, and the magnitude of the vector is the same. In this course, in general, we will locate the vectors at the origin of the reference frame. Well, you can multiply a vector in Rn by a scalar in R. So C here is a real number, and you can simply do that by multiplying each of the elements of V by the constant C. Okay, so the vector W that is obtained will be in the same direction if C is strictly positive. Okay, what will change, of course, is the magnitude of the vector. So if C is strictly positive, W and V are called collinear. Well, if C is a real number, what could happen is that it's negative. If it's negative, of course, W defined as C times V will be in the opposite direction. Okay, so if C is general, all we can say is that V and W are parallel. You can represent a line, and in this case it will be a line that goes through the origin by a vector multiplied by a scalar C. Okay, and the vector V here will give the direction of the line. So we have here represented our vector V with coordinates -1, 2, and we'll see what happens if we want to look at 2 times V. What you have to do is take each coordinate separately and multiply by 2, and you obtain the vector that is represented, that is shown over here. And you can see that it's in the same direction as C, which is equal to 2 here, is positive, but the magnitude of the vector is multiplied by 2. Let's have a look at minus V here. Minus V, well, you see that the coordinates have been multiplied by -1, and the constant C here is -1. The length has remained the same, but the direction is opposite. Well, of course, you can add vectors V and W that are living in Rn, and this is simply done by adding their respective components. Okay, it's kind of obvious that you can only add vectors if they have the same dimensions. Okay, so they have to be what is called compatible. I'll give now an interpretation of vector addition, and I'll start from the vectors V and W that I've shown before, and I want to represent the vector sum. Okay, so there is a first algebraic interpretation which consists in adding the elements of each vector component by component, and this produces a vector which has components or coordinates 2, 4, and this is this vector over here. As I said, this is a more algebraic interpretation. Well, the second interpretation is more geometric in nature, and it's using the so-called parallelogram rule. So what you do is place the two vectors head to tail. So we'll take, for instance, an equivalent vector to W, and we'll place it over here. So the head of this vector that is equivalent to W is placed at the tail of the other vector, and the resulting vector is shown over here. It goes from the free head to the free tail. Okay, so you could do things also by taking an equivalent vector to V and place it over here. Okay, and of course you end up with the same result. So instead of adding the two vectors, I could be interested in their difference. Okay, V minus W, and this can be rewritten as V plus the vector W, that is multiplied by -1. Okay, so I'm combining vector multiplication by a scalar and vector addition. Okay, so if I want to obtain minus W, I have to multiply the vector by -1. I obtain a vector of the same length but in opposite direction. Okay, so now I have to do the addition of V and minus W. So I'll place my vector minus W at the tail of my vector V, and I know that the resulting vector goes from the head of V to the tail of minus W, and the resulting vector is this one over here. If we're interested in the vector W minus V, there are two ways to proceed. We can start from the vector V minus W and multiply it by the scalar -1. We know that it will produce a vector in opposite direction with the same length, so it will produce this vector over here. Another way to work is to do as we did previously. So we first construct the vector minus V, we place it at the tail of the vector W, and we do the vector sum, and we obtain the expected vector. Well, we can of course combine the operations multiplication by a scalar and a vector addition, and we obtain what is called a linear combination of two vectors. So you take the first vector multiplied by the scalar C, and you add the second vector multiplied by the scalar D. So C times V plus D times W is simply obtained by doing the same operation on each element. Okay, and as I've said, this is called a linear combination of two vectors for some constant C and D, which are living in the set of reals, so they are real numbers. Okay, so if you take linear combinations and all linear combinations of two vectors in our square that are independent, which means that they are non-parallel, you generate the whole plane. Well, let's take two vectors over here. This is a vector and this is another vector, and let's call it V and W as in the slide over here. And if I take all kinds of linear combinations, let's take an example. I'll take a linear combination, I'll multiply V by a half, So this produces this vector over here, and I multiply this one by minus a half, so this produces a vector that goes into this direction. And now I add the two, this will produce the vector that is over here. Okay, so here I have used c is equal to a half, and have used d is equal to minus 0.5. If I do this for all real numbers c and d, I can generate any vector in R square. So I'm generating the whole plane. Well, you can extend the idea from R square to Rn. So if you take n independent vectors in Rn, and you take all linear combinations of these n vectors in Rn, well, you will generate the whole space Rn. Suppose now that instead of taking n vectors, n independent vectors, you take m, and of course m is smaller than n. Okay, so you have m smaller than n. And you take these m vectors that are independent, and you take all possible linear combinations of these vectors. They will of course not produce the whole space Rn, but a subspace. Okay, so let's take an example and take n equals 3. Okay, so this is, well, space, right? You work in space, and you take m equals 2. So let's imagine that you take two vectors that are independent. Okay, for instance, you take a pen or two pens, and you point them into different directions, and then you start to imagine all possible linear combinations of these two vectors represented by these pens, and you will see that you will be generating a plane. Okay, so a plane is the subspace of R cube. So a non-empty set on which addition is defined and scalar multiplication is defined is called a vector space if the following properties hold for every vector u, v, and w, and for every scalar c and d, which are reals. Okay, and the properties are commutativity. Okay, so the vector sum is commutative. Associativity. There exists a zero vector, so if you add any vector to 0, you obtain the same vector. Every vector has an opposite vector, so that you can produce the zero vector. There are three properties of distributivity. Distributivity with respect to scalar multiplication, and there is also an identity element for scalar multiplication. This corresponds to c equals 1. Well, if you take the sets Rn and Cn, you can show that there are vector spaces, because the properties that we've seen in the previous slide hold for these sets Rn and Cn. But very different sets can be vector spaces. For instance, if you take the set of all continuous functions f of x, where x is defined on the interval minus infinity, infinity, it is also a vector space. Because if you take two functions in this set, okay, and you start taking linear combinations of these two functions, well, you'll obtain continuous functions, okay, defined on the same interval. Okay, so this produces a vector space. You can do the same, for instance, with the set of polynomials of degree at most n, and show that it's also a vector space. The set R plus, which is the set of all strictly positive real numbers, is not a vector space. Okay, So this is 0, it's not contained, and then you take all positive real numbers. Well, it's kind of obvious it's not a vector space because there is no element in R plus that can produce me the origin, okay? Because this would take me to something that is negative and it's contained in the set. So R plus, for instance, is a counter example. It's not a vector space. So we can generalize something that you know, which is the scalar product to Rn. It's called scalar product because it produces a scalar, but sometimes you will see dot product or inner product in English. So the scalar product of two vectors v and w in Rn is simply obtained by multiplying component by component and then by adding the results. Okay, so plus plus plus, and indeed you obtain here a scalar. This is why it's called the scalar product. You know that there is also a vector product that will produce a vector. Well, the dot product or scalar product is commutative, so v scalar product with w is equal to w scalar product with v. And you know, this is a property that you know already and that can be extended, of course, to Rn. If the dot product of two vectors is equal to 0, this means that these two vectors v and w here are perpendicular. Sometimes the dot product is written a little bit differently. So v dot w is the scalar or dot product, but it can be written in terms of vectors. Okay, remember here that the vectors v and w are column vectors. So to make the vector or matrix multiplication compatible, you can write it either as v transpose w or w transpose v. Okay, if you multiply v transpose by w, indeed you end up with this result here, and this is equivalent to the scalar product as denoted here. Well, the scalar or inner product comes with a certain number of properties, and these properties are that for any vector u, v and w in Rn and any scalar c in R, well, you have a form of distributivity with respect to vector addition, a form of distributivity with respect to scalar multiplication. We had already seen that the scalar product is commutative, and also we can show, it's not very difficult, that the scalar product of a vector by itself is positive or 0. Okay, and it can only be 0 if the associated vector is the 0 vector. So we have seen previously what a vector space is. If it is equipped with an inner product, we'll call it a Euclidean space. Okay, so Rn, for instance, we've seen that it's a vector space, and if it's associated with the inner product or scalar product that is defined in the previous slides, well, you can show it's a Euclidean space because it's a vector space equipped with an inner product. Well, we had already seen that Cn is a vector space. So I'm now considering this part of here. So Cn is a vector space. So if you define a dot product or a scalar product on Cn, well, then you obtain an Euclidean space. And if v and w are vectors in Cn, their scalar product is defined as follows. Okay, so it's very similar to what we had used on Rn, but you have to take complex conjugates. Okay, so Cn is an Euclidean space. It's a vector space associated with this inner product or scalar product. And if you look at the properties of this dot product, you have to change the third property over here. And if you work with complex vectors, this property becomes this one over here. So you have to take the complex conjugate when you take the commutativity property. So the norm or length of a vector in Rn is defined as the square root of the scalar product of that vector by itself, and by the definition of a scalar product, this yields this formula over here. This is something that you know already, and let's consider an example in R2. Okay, so we will draw here a reference frame and draw a vector, which is this one over here, and it has coordinates v1, v2. Okay, and by the Pythagorean theorem, it's kind of obvious that the length of this vector is the square root of v1 squared plus v2 squared. So you can define the notion of a vector with unit length or with length 1. And if you're given a vector in some direction, you can give it a unit length by simply dividing by the length of the vector. So this is something that we'll be using quite often in this course. The Cauchy-Schwarz inequality states that for all vectors u and v in Rn, the following property holds. That is to say, the absolute value or modulus of the scalar product of these two vectors is smaller or equal than the product of their respective lengths. Okay, if these vectors u and v are parallel, you have equality in the equation that you see. And if the vectors are collinear, they are parallel but they point in the same direction, then you can have equality without the absolute value in the equation. So let's prove this Cauchy-Schwarz inequality. You will see that it's not that difficult. Of course, you can also skip this proof. As you see, it is for your information. So let's have a look at the vector tu plus v. And here u and v are any vectors in Rn. It says u here. It does not mean that u is of unit length. Okay, so it can be any vector. And t can be any real number. And let's have a look at the length of this vector squared. And of course we know that it's positive or 0. Okay. And this length squared, we can rewrite it like this using the scalar product. Now we can go from one equation to the other by the properties of the scalar product, and more in particular the property of distributivity, and we end up with this second order polynomial in T, where A, B and C are defined as follows. Okay, so here A is positive or 0. Okay, well, by the properties of a second order polynomial, you know that if there are real roots, different real roots, since A is positive, you will know that the polynomial will be positive outside the roots. Okay, and it will be negative in between these real roots. Okay, this is something we do not desire. So we know now that we cannot have two different real roots. This means that the discriminant squared, rho squared, must be negative or 0, or equivalently that b squared must be smaller or equal to 4ac. If you take this condition and you plug in a, b and c, you end up with this equation over here, And this is equivalent to saying that the modulus of the scalar product of u and v is smaller than the product of the length of u by the length of v. And this is indeed Cauchy-Schwarz inequality that we have just proven. Well, we can also prove the Minkowsky or triangular inequality. And this inequality says that for any vectors u and v in Rn, and again u does not need to be of unit length, the length of the sum of two vectors is always smaller or equal to the sum of their respective lengths. Well, this can be proved quite easily. Let us look at the squared length of u plus v, and this can be rewritten like this by the properties of length, and then you go to this formulation here using the distributivity property of the scalar product. We have just proven the Cauchy-Schwarz inequality, which is this inequality here, and of course modulus is always larger or equal than what is inside the modulus. Okay, so what we'll do is replace this quantity over here by something that is larger. Okay, so you end up with this thing here being larger or equal than this thing here. Okay, and this you can rewrite like this thing here. So this is the sum of the length squared. We're almost there. We can remove the squares here, okay, because what is underneath the squares is itself positive, and we end up with the Minkowsky or triangular inequality. Well, in this slide we are interested in the distance between two vectors. So the first thing that you have to do is to compute the resulting vector u minus v. Okay, and u minus v is a vector with components or elements u1 minus v1, u2 minus v2 up to un minus vn. Okay, and now you can compute the length of this vector. This is this quantity. You know that it's the square root of the scalar product of this u minus v by itself. Okay, so this gives you this quantity over here. So now we have to take the scalar product of the vector by itself, and by definition this will give you this formula over here. Well, the angle between two non-zero vectors can be computed using this formula. It says here non-zero, otherwise you'll have a problem here at the denominator. So you can obtain the cosine of the angle by this expression over here. And for the cosine to be defined, you would expect this expression to be between -1 and 1, and this is indeed the case by the Cauchy-Schwarz inequality. Remember that the modulus of the scalar product of u and v is smaller than the product of the length of u by the length of v. Okay, so u v scalar product modulus divided by the length of u and the length of v is smaller than 1, and this is equivalent to this formulation over here. So this is indeed a valid equation. You will see that, as we had said previously, if the scalar product of u and v is 0, okay, so you have a 0 quantity over here, this means that the angle here is pi over 2. This means that the two vectors u and v are orthogonal or perpendicular. Well, here are a few examples of what we had seen previously. So here you're given a vector with elements -1, 2, and you can compute its length, okay, by the formula, but you see of course that this comes from the Pythagorean theorem. If we take two vectors v and w and we compute their scalar product using the formula, we see that it's 0, and indeed we see here that these two vectors are perpendicular. Okay, let's take two vectors that are obviously not perpendicular, and now we can use the formula of the previous slide to compute the angle. Okay, we know that the cosine of the angle is given by this quantity here, so we need the length of the two vectors, 3 and square root of 20, and we need the scalar product, which is 12. And you can obtain of course the angle by taking the arc cosine, and this gives us here an angle of 26.5 degrees. So we know that if the angle between the two vectors is 90 degrees, then the scalar product is 0. Okay, so this is indicating that the two vectors are perpendicular. If the angle between the two vectors is smaller than 90 degrees, okay, so it's smaller than 90 degrees here, the angle is acute, then the scalar product of the two underlying vectors is positive. Okay, and if the angle between the two vectors is larger than 90 degrees, okay, so the angle is obtuse, then the underlying scalar product will be negative. So in this slide we're talking about projections, and it's the projection of a vector u on a non-zero vector v, and it will be denoted like this. Okay, so this is the projection of u onto v, and this yields this vector that you see over here. Okay, so obviously it will be pointing in the direction of v, so we're taking a unit vector in the direction of v, and we obtain that by simply taking v and divided by its length. So we are working here in a right-handed rectangle, so we can compute this length over here, and this is simply the length of u times the cosine of theta. So if the angle theta is acute, this thing here is positive and u tilde is pointing in the direction of v. If the angle is obtuse, it will be pointing in the opposite direction to v. So we can now replace cosine theta by this expression here. Okay, so we can cancel out the length of u, and we obtain this expression here of u tilde, or this expression of u tilde. So this thing here is a scalar because it's a scalar product divided by another scalar product. So this is a neat way to compute the projection of a vector onto another vector, because you see that it only involves scalar products. Okay, so a scalar product, as you know, is multiplications and additions, right? And it does not involve the arc cosines or cosines and things like that. So it's a quite easy computation to make. We'll be using the notion of an hyperplane in Rn, and an hyperplane is defined as all vectors x in Rn that are perpendicular to a given vector n in Rn. Okay, so you can state this as follows, saying that you're looking for all vectors that are perpendicular to n, and this yields this equation over here, and you can rewrite this term as this one over here. Okay, So this is the notion of a hyperplane in Rn, and we can have a look, of course, at what that looks like in R2. So we'll be using our reference frame. So we'll be using the vector n, okay, and we look at all vectors that are perpendicular to this vector. So there is one over here, there is one over here, there's another over here, okay, and you see that this defines a line. Okay, so a hyperplane in R2 is simply a line. You can do the same type of exercise in R3, and you'll see that you'll obtain a plane. And in general, in Rn, we'll see that a hyperplane has dimension n-1. Okay, and we'll come back to this notion of dimension later on in the course. Well, the hyperplanes that we have considered, they go through the origin. It's kind of obvious when you look at this equation here that the 0 vector is indeed a solution of this equation. So we can also look at hyperplanes that go through x0, which is different from the origin. So here we have considered a situation in R2, but the formulas that we'll obtain will also be valid in Rn. So we're looking for the hyperplane that goes through x0 and it is perpendicular to n, and in R2 an hyperplane is a line. Okay, so the line that is perpendicular to n and that goes through x0 is shown in orange. Well, this hyperplane, this line here in R2 shown in orange, is obtained by putting vectors here head to tail with x0. And here we have an example. We have put a vector head to tail with x0 to produce the vector x. So this vector that we have put head to tail with x0 is, in this case, x minus x0, and it must be perpendicular to the direction n. Okay, so the condition is simply n scalar product with x minus x0 is 0, and any x that obeys this equation will produce me a vector that is on this line. So you can rewrite this as n scalar product with x is equal to n scalar product with x0, and this will call simply d. Okay, so n scalar product with x equals d is the equation of a hyperplane that does not go through the origin, at least if d is different from 0, and that is perpendicular to n. Okay, so now we can look also at the shortest distance of this hyperplane to the origin, and in our example this is the shortest distance, right? So we can use these projections that we had obtained before and project x0 on n, and in this case this will produce this vector over here, and obviously it's the projection is a vector that is in the direction of n, and what we'll have is x0 scalar product with n divided by the scalar product of n by itself. Okay, so this is going to produce me a scalar here, and in our case this scalar will be negative. Okay, so we're looking for the distance and the minimum distance of the hyperplane with respect to the origin, so we have to take the length of this vector. So this length will be x0 scalar product with n, and you take the modulus divided by the length of n squared multiplied by the length of n. Okay, and this is indeed this quantity over here. Okay, and this thing we can rewrite also as d. Okay, remember that the scalar product of n with x0 is d divided by the length of n. And this is indeed what you see here in the next slide.